my topic for tonight is the introduction to economic physics. I've studied for a few days what is the best perspective for us as the physics guides to unlock the door into economic physics. By coincidence, Professor Domesky has mentioned about some knowledge in complex systems lecture. Thus, I will begin with the Brownian motion and the one-dimensional random walk and some stochastic calculus, and based in which we will introduce the famous Black-Scholes models of option pricing. And you will see that the Black-Scholes models is an elegant and powerful model. It is complete efficiency and arbitrage-free and Gaussian distribution, in the sense that the stock returns are normally distributed. I also share with you the different perspectives to construct the Black-Scholes models, and just so similar to the reference frames transformations in physics, we can use different but equivalent martingale measure to simplify our calculations. And the following is for the first part. One-dimensional random walk means that if you consider a particle in the side of the x-axis, you jump to left or right with the same probability 1/2 with the same length of one step. You see that this random model will lead to the Gaussian distribution, which play a critical role in economic physics, and the notion of normal distribution. For example, m is the mean value of x, and sigma square is the square variations of x. And the modified Gaussian integral in the right side of the PPT will obtain some common mathematical expectations of x. And explicitly for the macroscopic procedure, it is just simple. Suppose that to reach to d, the particle has moved d plus steps to the right and d minus steps to the left. And then we take the notion of d and t. The probability that it reaches d through these steps is given in this formula. It is simple, the permutations and combinations operations. And if we consider n is far bigger than 1, we can approximate the factorial of n by Stirling's formula. And after some tedious but straightforward algebra, just with Stirling formula and the transformations of variables and Taylor series, we can simplify the formula and obtain the Gaussian distributions. If someone interested in a procedure, you can check it after the presentation. And I also written in my appendix. 哎，刘金，过来。在哪里啊？屏保一样，如果没有呢？这里等一下，有。And attached with the appendix, you can check the explicit calculations of the Gaussian distributions after the presentations. So, for now, you just believe me that we can obtain the normal probability distribution from the random walk. But it is just a discrete model. And how to merge this discrete picture with the description when we use continuous variables with the limitations. We have to introduce a probability density, the little p instead of the probability, the big P. And we should know that the probability is the mean behaviors of the region 2 delta x of the probability P. And with the change of variables and infinitesimal limitations of time interval and the length of delta x, and we take the notion of d, and we can obtain the Gaussian distribution in continuous pictures. But in the procedure above, we began with the discrete random walk model and changed to continuous picture with limitations to obtain the Gaussian distribution. Now, for a more direct perspective, we start the analysis from the continuous description directory. If at time tau, the particle's location is between x and x plus dx, and at time tau minus delta x, the particle can either between x minus delta x and x minus and plus delta x plus dx, and just say in the picture. And similar to the random walk, it has the equivalent probability from two locations in the last time. So we can obtain these equations and then take the Taylor series expansion of the probability density. And you can eliminate some terms, just like the p tau x in the both sides of the equations. And you can obtain the diffusion equation, and you can use the green functions or the Fourier transformation to solve this question. And you will obtain the Gaussian distribution again. So you would have no way to go through the discrete model first. And I should say there exists many perspectives for rest. For instance, from the view of transitions, let the probability distribution for this step be QL, and we assume that it will satisfy these two discrete formula, and you obtain the mean value and the square of variations of delta x, and you obtain the diffusion equations at last. So based on the Gaussian distributions, the standard Brownian motion or Vienna process should be introduced. It is a stochastic process with the following properties. The increment has a normal distribution for the mean value is 0, and the square variations, the standard variations is squared t minus s. And for the fluency of my presentation, some properties of Vienna process are used directly in the below procedure, and I will now supply the derivation of some probabilities. If you are interested in it, you can check it after the presentation in my appendix. And based on the Vienna process, we introduce the general stochastic differential equations. Just like the why we introduce this process. We are familiar with the payoff function of a bank account. Just like and we all know this simple formula is for the return of the bank account, and R is the rate of the payoff functions. But the stock is not so deterministic. If you have a fluctuation tone, and the Vienna process or the fractional Brownian motion for generic is the best model to describe the fluctuations, so we should introduce these terms to describe the fluctuations in the stock market. So one of the applications of Ito formula is to solve the geometric Brownian motion. So we first suppose have a new stochastic process J defined by a function of xt, and consider the Taylor expansion of the function fxt, and substitute the stochastic differential equations to df. You obtain the so-called Ito formula, and substitute SDE to the Ito formula. You can obtain explicit form of Ito formula, and as the following, I will mention that why we should obtain this Ito formula first. And we should introduce the geometric Brownian motion. Just take the change of x to t and a equal to mu s and b equal to sigma s. And we can obtain the stochastic process S. And the geometric Brownian motion is the basic model for stock price dynamics in the Black-Scholes plane. First, we should find the description function of the geometric Brownian motion. And as the general view, we always hope to realize the linearization of the equation with the separation of variables to solve the differential equations. And if we take this procedure like this, it is right or wrong? The answer is wrong. We can't do it like just so simple from 3 steps. Because in these properties are always kept. And in the general definition of limitations, the derivation of fx and this is the limitation definition of derivatives of fx. And take the Taylor series. You obtain this term is and so on and so on. And divided by delta x, and take the limitation of delta x to 0, and this term is rest. But for the fluctuation terms, the Brownian motion, the second power terms move back to the first power, the first order terms. So we can't take the general procedure like this. So we should we can see more explicitly in this procedure. And if we take the series of dj to the second order terms and just take the square of the geometric Brownian motion, and in the general views, this term will be yield 0 because we use the definition of derivatives like this. But the square of dw will supply like this, supply a first order term of dt, so it can't be neglected. In my general view, it's different, so we will obtain the dj is different from the original view. So we should use the Ito formula, and we know that a differential equation is actually a shorthand notation of the corresponding integral equation. Such the Ito integral does not conform to the usual integration rules from deterministic calculus. An example is the formula below, and in a similar way, we will obtain the 1/2 of the square of wt, and we can't see the second term minus half of t in the original integral. But when we introduce the Vienna process, it will appear. So it's the interesting point of the Vienna process integral. That's why we need the Ito formula before. And this result I give directly. And if you have the interest, you can check it after the presentation in my appendix. And just substitute A equal to mu s and B equal to sigma s to Ito formula, and take the change of J is equal to ln s. You can obtain the differential equations we have obtained in the bottom directories. And when we go through the integral operations, you can obtain this formula. And reverting back to the variables s, because J is equal to ln s, we obtain the explicit solution of the stochastic differential equations. And from the equations Jt, in the fourth line, Jt equal to J blah blah blah, and with some properties of Wt. I have no derived in the presentation because it is tedious. So you just believe me, this result is right. And we find that Jt is distributed according to a normal or Gaussian distribution. That's why I emphasize the Gaussian distributions at the first of my presentation for again and again because it's so important for the finance. This result can be used for the following procedure, and then the geometric Brownian motion with the initial value. You just substitute the J equal to ln s back to this formula. You obtain the log normal distribution of the stochastic geometric Brownian motion S. This is the rules of the change of variables and the conservation of the probabilities multiplying the region length. The geometric Brownian motion is the basic model for stochastic dynamics in the Black-Scholes framework. So, after we get the distribution of geometric Brownian motion, we go to the Black-Scholes models for option pricing. you see that the Black-Scholes model is an elegant and powerful theoretical construct. It is complete, efficient, and soon we'll introduce what is the complete of a model. And it is so similar to the physics about the vectors expansions. And it is efficient, arbitrage-free, and Gaussian, as we see above, in the sense that the backstop returns are normally distributed. Suppose that there are two assets in the market, a bank account B and stock X, and the price dynamics just like this. The first equations we are familiar with because it is deterministic with no fluctuations. And the second is the geometric Brownian motion with the fluctuation terms dw. And R is the risk-free interest rate, and mu is the stock mean rate of return. Sigma is the volatility, and Wt is the Vienna process. Let us then denote the CKT. Let's just first neglect the meaning of KT. You just see this as a parameter. Because if I interpret it, it will take some time. And then according to Ito formula I have introduced above, and with A equal to mu s and B equal to sigma s, just substitute to the Ito formula, you obtain the following dynamics. C is equivalent to F. Then we consider the self-financing delta hedging portfolio, a long position in the option and a short position on dollar stocks. You just focus on the mathematical equations, it is okay. And pi t is equal to CST minus delta S, and take the differential operations and substitute ds, dc, and ds to the formula. We obtain these equations. We can eliminate the risk. The risk is the terms dw, the stochastic term containing dw. And from this portfolio, by choosing delta and take the delta is equal to partial C partial S. Inserting this formula back into the formula above, we then find the equation of pi with respect to t. Since we now have a risk-free portfolio, we must yield the same rate of return as the bank account. And this, the red letters is according to the basis theorem in finance. And from the blue box above, you just remember the equation R equal to R spot, and the rest you should neglect it. If you have interest in it, you can have a look. And R equal to R point spot, it means the same rate of return as the bank account. So, which means the D pi is equal to R pi dt. And then we obtain so-called Black-Scholes equations with the boundary conditions. And these boundary conditions is according to the definition of a call options. So, and the next step, we will solve these equations with the boundary conditions above. And its basic procedure, you can check in my appendix. And as a total result, it's like this. And the nx is the cumulative distribution functions. And this is the components of the Black-Scholes model. We can replicate the European coefficient CST using an appropriate self-financing portfolio in the BS market. And the BS is so similar to the basics vectors expansions in the quantum mechanics, and whose value Zt equals to option CST for all time. T is smaller than T. And now we should solve the equations to find what is the X and Y. And based on standard model of finance, the change of the value only respect to the change of the class of the stocks, and we have no relative with the xt. And it follows that substitute ds to the dz, and we can also these dynamic differential equations, and then we could find the value of y and x. And then is this again the Black-Scholes equations, what we have derived above. We have seen that it is possible to replicate a European coefficient CST using an appropriate self-financing portfolio in the BS market. The derivation of the BSE presented there must hold for any contingent claim. An arbitrary European contingent claim will pay off ST, and this is the boundary conditions. And we retracing the steps outlined in the derivation of the Black-Scholes equation. It follows that it is the general form of the Black-Scholes equations. And when we express this result in terms of the original variables S and T, yields a generalized Black-Scholes formula. So that's why we said the Black-Scholes model is complete. Comparing the generalized BS formula above with the probability distribution functions we have derived in the previous subsections of the geometric motion, it follows that FST can be expressed in the last formula. And why I write these equations? Because I want to introduce the martingale theorem. And this is the next foundation theorem of finance. Is the market said to be efficiency if there exists at least one probability measure Q equivalent to P, such that with the time transformation, it will be the same on the time t, and s divided by b, this value will be the same with the transformation of t. And this is the first fundamental theorem of asset pricing. And implicit symmetry principles are intimately connected with conservation laws. It is thus only natural to ask whether the efficiency symmetry, just like the times transformations, make no sense to the discounted prices. To ask whether the efficiency symmetry above also leads to a conservation law. Perhaps not surprisingly, this is indeed the case. The first fundamental theorem of asset pricing tells us that the absence of arbitrage cannot be interpreted as a kind of conservation law for the vacant state of the money. If you start in zero initial money and do not take any risks, then you will remain at this state for all times. And we'll change the equivalent martingale measures, just like the transformation of frame in physics. The notion of an equivalent martingale measure can be used to price the derivatives in a rather direct way. Without having to solve a PDF means that the probability differential equations with some so tedious calculations. The idea is that in an efficient economy, all financial assets are martingale with respect to the equivalent martingale measure Q. And the martingale measure Q should satisfy the conditions below, as we have mentioned above. And if the bank account return functions B equal to B0 ERT, and we will obtain the FST can express in the expectation of the boundary functions of S and T. And the FQ denotes the probability density under the equivalent martingale measure Q of the process ST with initial value as 0. And we just need to find the martingale measure Q and consider the process, and this means the discounted price and take the differential of dj. And we would, if we take a change of Wt to a new linear process with this form, we would take the dj to a standard Brownian motion. In something like the reference frame transformation in physics, we should find a martingale measure Q, under which the process Jt should be a martingale. And what is the martingale? It should satisfy in the mathematical formula. The expectation of Wt in the filtration of Ft should be a constant, and with no respect to the t. So the Wt0 is a constant. But if you have the dt term, it will with respect to t. So let me change the Wt, the dj, and estimate the dt terms. So that's why we change the linear process to a new process. And therefore, geometric Brownian motion is not martingale because I mentioned above, it has dt terms. And this expectations is not a constant. So we should make a transitions and substitute a new linear process to the geometric Brownian motion, and it follows that a new geometric Brownian motion, but with a new mean return R, and there is the VRT, the measure Q. The price ST follows a geometric Brownian motion with the mean rate of return equal to R. And similarly, we will obtain the distribution functions like the PST in the original martingale P, and just substitute to the FST. We can obtain Black-Scholes equations without solving the PSE. And from this generalized form of FST, we can obtain the Black-Scholes formula in a more direct way. In a word, after introducing the Gaussian distribution and Ito formula in general stochastic process and the geometric Brownian motion, we reach a fundamental and important pricing model, the Black-Scholes model. And then we introduce different perspectives to derive Black-Scholes model to solve the stochastic differential equations in the original martingale measure, or with a more direct way on another equivalent martingale measure Q to find the value of stock price with respect to time. CST is the fundamental problem in economic physics. I chose this plan, though it is a little boring because it is somewhat reminiscent of the reference frame transformation and the basis vectors expansions in physics. By the way, I can introduce some notation and fundamental theorems in finance. And so, thank you. That's all.